This is a short section, and its aim is two special real-valued functions on the space of linear transformations, the trace and the determinant. Both send a transformation to a number, and both are independent of the choice of basis. The trace first. Theorem 5.1. On an n-dimensional space, there is exactly one linear functional unchanged when two transformations swap places in a composite and giving n on the identity. In any basis, it is the sum down the main diagonal. Existence is easy. Choose a basis and define the functional as the diagonal sum. Linearity is clear, and the identity gives n. For the swapping property, write out the entries of the composite and exchange the two summation indices. The two sides agree. Uniqueness goes like this. Through the isomorphism with matrices, it is a functional on the matrix space, so a set of coefficients gives it. The swapping condition forces the off-diagonal ones to vanish and the diagonal ones to agree, and the identity fixes the size. So the functional is unique, and it is called the trace. Note what happened. A basis was chosen to define it, and the theorem says it does not depend on that choice. That is the real reason the trace is independent of the basis. Now the determinant. It is much more complicated, and the book says its existence is not proved until chapter 7. The geometric meaning can be given now, though. Its absolute value is the factor by which the transformation multiplies volume. The sign records orientation. It is positive when the transformation preserves orientation and negative when it reverses one. Orientation itself is explained later. For now, read it as whether left and right have been swapped over. The book assumes the determinant exists and lists 5 properties. First, the determinant of a composite is the product of the determinants. Second, a shearing has determinant 1. A shearing slides the space along planes parallel to a subspace, no layer deforming. Third, when the space splits as a direct sum of invariant subspaces, the determinant is the product over the pieces. Fourth, in one dimension the map multiplies by a constant, and that constant is the determinant. Fifth, swapping two independent vectors in the plane gives -1. Theorem 5.2 gives the two-dimensional formula. The product down the diagonal minus the product up the other one. It is a special case of a general formula with n factorial terms, each a product of n entries. Impractical for large n, but fine for 3. 3 last results. Transposing leaves the determinant alone, and so does carrying the map elsewhere by an isomorphism. A map is invertible exactly when its determinant is not 0. Finally, Kramer's rule. Replace the jth column by the right-hand side and take a ratio.